Hi there. So in this section, we're going to be looking at probability. And so in association with probabilities, there's a few little bit of terminology that we want to get down. And so that's where we're going to start here. So the first is your sample space. And that's a list of all of the possible outcomes in an experiment. So the example that I gave you underneath here, well, if you toss a coin, that would give you two possibilities, right? Heads or tails. Tree diagrams are a nice way to give you a visual representation of a sample space. So I'm going to definitely go through an example of that with you so that you can see what that looks like in terms of performing an experiment and then seeing a full sample space being listed out. And then associated with the tree diagrams will be the counting principle. And the counting principle will be a way in which we can determine how to set up our tree diagram. But even more broad scale than that, it tells you the number of ways an experiment can happen. So like I said, it's used to determine the total number of possibilities in an experiment. If the first step in your experiment can be performed in m distinct ways, and your second step can be performed in n distinct ways, then the two experiments in that particular order can be performed in m times n distinct ways. And of course, I'll be demonstrating that for you here in just a few moments. And then a big formula that we need to be conscious of for this particular section, so it's like I said, we're talking about probability, is, well, how do we calculate the probability of an event? And the probability of an event is equal to the number of ways that that event can happen divided by the total number of outcomes in your sample space. So that's why it's going to be really important that we're aware of what our total sample space is. All right, so I'm going to start us down here below in example 1 and example 2, just talking about that counting principle so we can, just start thinking about, well, how many ways can a particular experiment happen? All right, so in example 1, I've got this one, labeled out for us, okay? So we kind of talk through it and break it down, okay? So here in example 1, it says to determine the number of points in the sample space, if we were to pick a card from a deck of cards and then toss a coin, we would ask ourselves, if we were interested in the total number of points in our sample space, we would ask ourselves then, how many possibilities are there when you draw from a deck of cards? And so drawing from a deck of cards, let me get my pen back. And, if you're not familiar with the deck of cards is provided for you on the formula sheet for this course. But if you go back and look at that, there are 52 cards in a deck of cards. Okay. Then we want to know, well, how many possibilities are there when you toss a coin, right? You can get heads or tails. There's two possibilities. Those are our two experiments. So we're going to multiply 52 times 2, and that would land you at 104 different possible outcomes if we were to draw from a deck of cards and then toss a coin. All right, so coming on down to example 2, I would like to look at letter A, D, and E with you, and then let you go back and fill in B and C from the solution key. First try it on your own and then check yourself by the solution key. All right, so in part A, it wants us to find, well, in example 2, all of these, they want us to determine the number of points in our sample space. Part A wants us to toss 2 coins. So I'm going to draw myself 2 blanks, right? I'm going to label it underneath here as this is tossing coin 1 and this is tossing coin 2. When you toss that first coin, how many possibilities are there? And hopefully you agree. There's 2. When you go to toss that second coin, how many possibilities are there? Still 2, right? Heads or tails, eat both times. So then in the end, 2 times 2 will get us 4 total possibilities as a final answer. Okay, we're going to be utilizing this here on the next page when I'm going to step this up with our tree diagrams and then start actually calculating a probability. Move on down then to letter D. I want us to choose 2 letters from the alphabet with replacement. So in letter D and E, I just want to go through and demonstrate for you the idea of with and without replacement. When you say with replacement, then that means, I'm going to go down here and I'm going to draw my 2 blanks because I'm drawing 2 letters, and I'm going to put underneath here, I'm choosing letter 1 and letter 2. When we say with replacement, when I go to choose letter 1 from the alphabet, how many letters are there in the alphabet? Well, you agree, there's 26. With replacement then means that once I choose that letter, I'm going to look at it, I'm going to note what it is, and then I'm going to put it back so that when I go to choose again, I still have that letter is still in play, and so when I go to choose letter 2, I still have 26 letters to choose from. And so then we would use 26 times 26, and that would get you 676 different possibilities. All right, so now let's compare that to letter E. I'm still choosing 2 letters from the alphabet, so I'm going to draw my 2 blanks. letter 1 and letter 2, but this time without replacement. And without replacement means when I choose that first letter, I'm still going to have all 26 to choose from, right? But now it's without replacement, so I'm not going to put it back. And so now when I go to choose my second letter, I'm going to have how many left to choose from? Hopefully you agreed. I only have 25 letters left to choose from. So now 26 times 25 would put you at 650 total possibilities. I'm just going to abbreviate there for possibilities, okay? And the note that you'll see down here below, we can use this counting principle to help us set up our tree diagrams, and that's going to enable us obviously to get a full sample space. And then I think it gives you a nice visual, if you're a visual learner, helps you to answer those probability questions more efficiently. All right, so I'm going to flip it on over. I'm going to do example 3 from top to bottom with you, and then let you try example 4 on your own because it's also a tree diagram. So here in example 3, it says that a store offers 3 different colored shirts. You can get a white shirt, black shirt, or red shirt. And they're either short-sleeved or long-sleeved. You can also choose whether you want a pocket or not. And it wants us to use a tree diagram to determine all the possible types of shirts that you could buy. So in part A, it says use your counting principle to determine how many possible shirt types exist. So if you come underneath here, I kind of try to get you started here, right? They're selling them by the color, by your sleeve length, and whether you have a pocket or not. So how many color choices were there? Black, white, and red. So there's 3 color choices. Sleeve length, they tell you it's either short or long. So you've got 2 choices there. Pocket, you can either get it with a pocket or not. So 2 choices there. All right, so we're going to multiply here. 3 times 2 is 6. 6 times 2 is 12. All right, so I should end up with 12 different possibilities in my sample space. All right, so like I've been alluding to, this counting principle here is going to tell us how to construct my tree diagram. So the tree diagram always starts with a single dot here on the outside, and then it tells me to branch off 3 times. So I'm branching off 1, 2, 3 times, and this is going to represent my shirt color, right? And I'm just going to abbreviate here. We can have a white shirt, a black shirt, or a red shirt. Okay, so that represents your shirt choice, your shirt color choice. Then we got a sleeve length choice. So now my counting principle says from each one of those branches, branch off twice. And then you're going to put your sleeve length, right? So you can have short sleeve or long sleeve. So I'm going to use S and L, short and long, short and long. Now from each of those, we're going to have pocket or not a pocket. So I'm going to branch off twice again. My final tree diagram here says branch off twice again from each of those ending branches. Pocket or no pocket. So I'm going to do P for pocket and N for not. So P and N off of each of those. All right. Now, if you go through at this point and count the number of ending branches, you should land at 12. So if I count to the end here, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so we're tracking there. Now, when you go to read this tree diagram, you want to read it like you read a book from left to right, top to bottom, okay? So I can have a white shirt, short sleeves with a pocket, white short sleeves with a pocket, or I could have white shirt, short sleeve, no pocket. All right, and so now I've exhausted that top branch, but notice how I can have white shirt, long sleeve pocket, white shirt, long sleeve pocket, or white shirt, long sleeve, no pocket. All right, and then I'm going to continue on now. I'm going to move down now to, I've exhausted now the full white shirt combinations. Now I'm going to come to the black shirt combinations. I can have black shirt, short sleeve with a pocket, black shirt, short sleeve, no pocket, and I'm going to continue on. And then I move to my red shirt. Red shirt, short sleeve pocket, red shirt, short sleeve, no pocket. Long sleeve now. Okay, all right. When you count here now, you should also have 12 total points in your sample space. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you've got total 12 points in your sample space. Oh, well, part C wanted me to list out my sample space. I just did that over here on the right. I need more room anyway, okay? All right, so part D now says, from this sample space that we've listed, it wants us to find the probability, find these following probabilities, okay? So now remember, probability is always the number of times that the event happens out of the total number of points in our sample space. So we know that our denominator here is going to be 12, right? Because it says, find the probability that a person selects a red short sleeve shirt with a pocket. So I come up here, red short sleeve shirt with a pocket. That only happens one time out of those 12 possibilities. All right, so I'm going to come on down to number 2. Find the probability that a person selects a white shirt. So I come up here, any combination up here. It doesn't say, it doesn't say whether they have to have short sleeves or long sleeves. It just says that they have to have a white shirt. Excuse me. So hopefully you agree then. These top 4 up here all have a white shirt, and those are the only ones. So I would come down here and say, okay, well then my probability is going to be 4 out of 12. Probability is always a reduced fraction. So 4 divided by 4 is 1. 12 divided by 4, give me 3. So 1/3, final answer there. All right, number 3 wants the probability that a person selects a long sleeve shirt. All right, so let's come up here, count all of the long sleeve shirt possibilities. So I'm going to erase those. All right, so any combination up here that has long sleeves, and so here, all of these over here on the right for me all have long sleeves, and so that's 2, 4, 6 out of 12. That can be reduced. Divide by 6 is 1, divide by 6 is 2, so 1/2, final answer. Again, probabilities are always reduced fractions. All right, number 4, probability that a person selects a black shirt or a shirt with a pocket. All right, so or means you can have one or the other or both, you just don't double count. So I'll say that again. I have a black shirt or a shirt with a pocket. I can have one of these or the other, or perhaps both. I'm just not going to double count. So I'll come up here and demonstrate that. So as long as I have a black shirt, so I'm going to come through, black shirt, put those in. Okay, so I've got those 2 and these 2, right? All right, so let me knock those off. All right, so those 4 are in play because they have black shirts or a shirt with a pocket. So I can come up here and I can pick up this one, this one, this one. I will not pick these up because I've already counted them as black shirts, but I will pick up that one. Okay, so that's what I meant by not double counting. I counted these first because they had black shirts. Okay, I picked up these 2 up here because they had a pocket. I picked up these 2 down here because they had a pocket. So as long as I have a black shirt or have a pocket, I get to be counted. And so that gives me 2, 4, 6, 8 possibilities down here out of 12. Can reduce that, divide them both by 4, would give me 2/3, final answer. Now let's compare that down to number 5, probability of a person selecting a black shirt and a shirt with a pocket. When you use that word and, then that means that you have to have both of those criteria met in order to be able for it to be counted, okay? So both of those criteria have to be met. I have to have a black shirt and it has to have a pocket. So I'm going to come up here and I'm going to erase these, and then let's think about it. I have to have a black shirt and it has to have a pocket. I've got to satisfy both conditions. So hopefully you agree. Okay, I can count this one for sure. Got a black shirt and a pocket. And I can count that one. It's got a black shirt and a pocket. But those are the only 2, right? That have both a black shirt and a pocket. So 2 out of 12, reduce 1/6. Final answer. Okay. All right, so I'm going to let you flip it over. It would probably be a really good idea to definitely pause the video now. Try example 4 on your own. Check yourself by that solution key. And then I'm going to go ahead and scoot us back to the very last page. And then on this page, we're just going to look at some other examples of how you can be asked about in terms of probability. All right. So example 5 says is looking at a spinner, and it says using the spinner, calculate the indicated probabilities. The key or the trick to a spinner is that if it's not already evenly divided up, it needs to be evenly divided up first, because you can see here your yellow space has a smaller likelihood than this red space down here. Okay, so what you want to do is you want to divide your spinner up by the smallest space. So in our case here, that small space would be all of these four up here. They're all the small. So hopefully you would agree then that I can come down here and divide these in half, right? And so then I can think of, okay, well, this space red, blue, green, yellow. Both of these down here are red. Both of these are blue, right? So just divided it up like that, okay? So now when I come over, I'm going to do A and B with you. I want the probability of it not being blue. So any other color on this spinner will work for me. So it's not blue. So it's going to be 1, 2, 3, 4, 5 out of my total. How many now wedges do I have on my spinner here? 4 up top, 4 on the bottom. So 5 out of 8. Okay. Come on down to letter B. Probability of my spinner lands on green. If you look around your spinner, there's only one green wedge, so 1 out of 8. Final answer. Again, these you'll always reduce if you can. Okay, I'll let you try C and D on your own. Example 6 is an important one, so I'm going to do example 6, all of these examples here with you. This is drawn from a standard deck of cards, like I mentioned to you. If you're not familiar with the deck of cards, that is available to you on your formula sheet. There are 52 cards in your deck. There are 4 suits. You've got your spades, clubs, diamonds, and hearts. Your spades and clubs are known as your black suits. Diamonds and hearts are your red suits. There are 13 cards in each of those suits. Ace through 10 are considered your number cards. We consider ace a low number card, so essentially it's a 1. Jack, queens, and kings are your face cards. All right, so with that said, we are drawing one card from a deck of cards, so one card out of our 52 cards. We want to find the probability that that card drawn is a club. So if you're looking on your formula sheet, how many clubs, or if you're, what you already know about a deck of cards, how many clubs are there in a deck? Hopefully you agree. There are 13 out of the total 52 cards. That can be reduced. Divide them both by 13. You get 1/4. Final answer. All right. In part B, probability of drawing a red spade. So if you look on your deck of cards, spades is the black suit. Can any of those be red? No, that cannot happen. So that would be 0. And you can think of that as that would be 0 cards out of my 52, and 0 divided by anything is 0. So that event cannot happen. You can never draw a card from your deck and get a red spade. All of the spades are black. Okay. In part C, and what's the probability that I get a 7 or a queen? So as long as, like I said, with the same thing with the or here, one or the other or both, just don't overcount. Okay, so how many 7s do you have in your deck? Hopefully you agree, there's 4 of them. How many queens are in your deck? Also 4 of those. So add that together, you got 8 total cards out of 52. Reduce, you can divide them both by 4. We get 2/13. Final answer. All right. Come on down to letter D. I want the probability that I get a heart or a 5, right? So I ask myself then, how many hearts are there in my deck? That's a full suit, so there's 13 of those. Now, I want to get a 5. Now, think about it. One of those 5s has already been, there are 4 5s, but one of those 5s has already been counted with the hearts. So I only have 3 left. And so then that lands me at 16 out of 52. All right, that can be reduced. Divide by 4 is 4. Divide by 4 is 13. So I got 4/13. Final answer. All right, move over to letter E. Probability that it is not a red queen. So ask yourself then, how many red queens are in that deck? Hopefully you agree. There's 2 of them. You got the queen of hearts and the queen of diamonds. So you've got 2 red queens, and that means all of the other cards are not red queens. So that would be 50 out of 52. Divide them both by 2, you get 25 out of 26. Final answer. All right, and letter F, probability that we get a red card or a black card. Okay, so think about it. You're drawing one card. It can either be, whenever you draw from your deck, it could either be red or black, right? So you've got 26 reds and 26 blacks for a total of 52 out of 52. Any number divided by itself is 1. That's an event that has to happen. When you're drawing from a deck of cards and you're drawing one card, it's either going to be red or black, right? All right, so let's come on down to example 7. Example 7, I'm going to do letter A with you, and I think then you'll follow. Well, actually, I'll go ahead and do all of example 7 with you. I'll do all of example 7 and 8 with you. All right. So in example 7, it says that a pet store randomly selected 150 customers entering the store and asked them to state their favorite type of pet. So out of the 150 customers that they surveyed, 75 favored dogs, 60 favored cats, 4 favored guinea pigs, 3 like ferrets, and the rest like birds. So I want us to find these probabilities, okay? Find the probability that a person favored dogs. So we base that off of what's already been observed. So we know that 75 favored dogs out of total number of customers, 150. Need to reduce that, and that should get you down to 1/2. Final answer. Okay. In part B, probability that the person does not favor birds. So that means then, so it tells, all it tells us up here is that the rest like birds. So we know then that the 75, 60, 4, and 3, add those together, that should put you at 142 over the 150. Yeah, and then I'm going to reduce that, and that should get you to, divided by 2, 71 over 75. Final answer. All right, in part C, I want the probability that the person would favor a ferret or a guinea pig. So how many, we've got 4 favoring guinea pigs, 3 favoring ferrets, so that'd be 7 out of the 150 customers. That cannot be reduced. That is your final answer. All right. And then lastly, like I said, we'll wrap up here with example 8 together. It says, if the probability of you winning a golf tournament is 1/5, what's the probability that you would lose? So think about it. What probability means is that this is the probability of you win. So you would win 1 time out of a total 5 tournaments that you were playing in. So what's the probability that you would lose? Out of those 5 tournaments, if you're going to win 1 of them, how many are you going to lose? Hopefully you agree. 5 minus 1, I'd lose 4 of them. Final answer there. Okay, so probability of you winning a tournament, you'd win 1 out of 5 tournaments that you played in. Probability that you would lose then, if you're going to participate in 5 tournaments, if you're only going to win 1 of them, that means the other 4 you would be losing. Okay? All right, so I will let you try finishing up the rest of this set of notes and checking yourself by the solution key. Thanks a lot. Bye.